classic problem incorporating the idea of conservation of energy, but now we're going to use gravitational potential energy and spring potential energy. So I know. Here's the problem. We're going to drop some object, let's make it spherical, all right, from some height h to a place where a spring is in its equilibrium position, right? And the spring has some constant k. All right, so now, from your experience, if I drop an object onto a springy platform like this right here, it's not just going to go clonk and stop, is it? What's going to happen? It's going to come down here and the spring's going to go, well, the spring's going to go boring, boring. Now they're separated, but you understand what's going to happen. It's going to depress it past its equilibrium point, and then it's going to come back up. Now remember this: if we just set the ball on top of the spring, it would compress a certain distance anyway, whether or not it had been falling, and that distance x would be equal to mg over k. Do you understand why it would just rest there in equilibrium? Okay, because in that situation right there, we would have the force, the spring force, which is equal to kx, acting upward would have to be equal to mg. Setting those equal to each other, we would get x is equal to mg over k. Right? Now, if we drop it from a height, though, what's going to happen to this spring? Is it going to go here, not as far, or farther when it brings the ball to rest instantaneously? Right. Intuitively, we can see that that's what's going to happen. It's going to compress it farther until it comes to equilibrium, right? And then it's going to push it back in the other direction. Everybody okay with that? All right. So let's think about what's going on with energy conservation when the thing comes back to rest. So we're looking at the situation at which, so we're going to call this h naught is equal to 0. So the compression of the spring is actually going to give it negative, so it's going to go downward from 0. Are we okay with that for a second? All right. So now we're going to release the ball, and then it's going to come down here, and it's going to hyper compress the spring. We don't really need to call it that, but a distance. The reason I said hyper, because it's going to be a distance that's farther than if we just had set the ball on there and let it sit there in equilibrium. Okay? So now it's down here like this. So now let's think about this. We have how many different kinds of energy? First of all, is energy going to be conserved?
Yeah. They're both conservative.
Spring is a conservative force, right? Springs are a conservative force. So we could talk about spring potential energy, and it'll be meaningful. So energy is going to be conserved. There are 3 different energies that we need to consider. We have kinetic energy, the energy of motion. We have gravitational potential energy, and we have spring potential energy. 3 different kinds of energy to consider here. All right, now, let me ask you a question. What's the speed of the ball when we release it from rest? 0. All right, so V naught is equal to 0, so what's the kinetic energy up here? 0. Good. All right, now, what about down here? What's the speed here when it comes to rest? So velocity is 0 again, so kinetic energy down here is still equal to 0. Now, in between here and here, it's sped up. Okay, I should have drawn it at an angle like that. All right, it's sped up as it came from here to here, and then it slowed down as it went from here to here, right? So however much positive work gravity did here, the spring's going to do negative work here, the same amount. But this is actually a little bit easier to do than thinking about it like that. All we have to do is our conservation of energy equation. So let's take a look down here, and we'll set it up nice and neat. We got kinetic energy plus potential energy gravitational plus spring energy is equal to K naught plus UG naught plus US naught. All right, so UGs are gravitational potential energy, US is our spring potential energies. All right, what's our first simplifying step? K's go away. Fruit ninja. Yeah! All right. So now, there's something else that is 0 somewhere in here. Be careful, because how many things are also 0? What's the do we have gravitational potential energy at the beginning? Or I'm sorry, at the end. Mg. This is a little spooky here. negative x. The question being asked in this classic physics problem, which I haven't even asked yet, is how far will the spring compress from its equilibrium position? So we're looking for this distance x right here. Okay? The amount of that the spring will compress. All right. Do you guys understand why it's mg negative x? What is the final energy, gravitational energy? If it would have been at 0, it would have been 0, right? So at the top here, it's mgh. Here, it would be 0. And down here, it's mg negative h. We actually have negative potential energy. It's a weird thing, but it's a function of where we take our 0 gravitational energy to be. All right, so we got mg negative x plus, what's the spring energy going to be? You guys remember what our relationship is with the spring constant? 1/2 kx squared. So this is the gravitational energy, and this is the spring energy. All right, at the top, what was the gravitational energy? mgh. What was the spring energy? The spring energy was 0, right? Because the spring was uncompressed. So this is what our expression is going to look like. And now we're going to set this up to solve for x. And you will take note. I will finish this after you guys go. So the video will still exist. Wait. I don't mean go now. But I want you to look at this. What do we have? We're trying to solve for x. We have a first order x term. We have a second order x term, and we have a constant. So how are we going to end up having to solve for x? It's going to be quadratic, right? And I'll finish it when you guys are gone. So this is in fact quadratic, but it's pretty simple to just mess around a little bit and say that we've got 1/2 k times x squared minus mg times x minus mgh is equal to 0. And we could multiply through by -1 if you feel like it. Doesn't matter. What we end up with is our a term for quadratic is going to be k over 2. To plug into the quadratic equation, our b term is going to be equal to -mg. And our c term is going to be equal to -mgh. And so whatever values we might be given, we would just plug them in, and we'd be able to come up with, we'd actually end up with 2 values for x. One of them would be nonsense because it would be negative, and that would be a situation where the spring had moved in this direction, which is actually physically possible, but the one we would be looking for would be the situation for when the spring had compressed a distance x from its equilibrium position.